Okay, before we start, I beg you to watch my very first video here. No one watched and no one left comment on it. So if you already watched this recommend video, if you leave like for this video, I will remake this video. If you subscribe and leave a comment, I will revamp this video for better version and better quality. So without any further ado, let's start our discussion video. For start, we recall the vector concept that vectors can be written as this, which is linear combination for component correspond to each arbitrary direction in geometric means spaces EI in n-dimensional vector space. And here, vectors can be rewritten as matrix because vector has matrix representation as this, as we know in previous video. And the next recall, we know about scalar, for example, Q as electric charge in electrodynamics and V as scalar field in previous video about vector calculus, which here, scalar has matrix representation as 1x1 matrix, as for example here Q, and for vector has matrix representation as 1x(n) matrix in n-dimensional vector space. And here's the question. One algebraic object that has maybe n×m matrix representation? The answer is yes and no. The answer is yes because it is related to some quantity in physics as tensor, and no for some reason in physics too. But here, we will focus on tensors. So, what is actually a tensor? In mathematics, tensor is just algebraic object just like vector. It lives in vector space, and the next construction relate to geometry in purpose. For example, scalar is 0 rank, vector is first rank, and the tensor itself usually denote for second rank, third rank, and so on. Scalar we can denote as just number here, and the vector we can denote as this as previous, but the tensor here we can denote as this summation, which this product notation is about tensor product, and EI, EJ, and so on in this is about basis of tensors, just like basis in vector. So in general, we can derive the nm rank tensor as this. Here, why we differ index placement? The different index placement, just like upper index here is denote a contravariant component, but for lower index here denote as covariant component. Which for example in vectors, we have this, which is the component of vector is contravariant, but the basis here is covariant. What difference between these two? Here, imagine we have coordinate system transformation that shrink the coordinate system. Here, covariant follow the transformation, and the contravariant here follow the transformation. Bruh. Just kidding. For the covariant here, transformation of covariant part is proportional to the transformation. Meanwhile, the contravariant part reverse proportional to the transformation. So here, if we have vector as algebraic object in our coordinate system, if the vectors stay the same thing, then by coordinate transformation, the length of vector getting bigger after coordinate transformation. So here the basis is shrinking, that's why it's covariant part, and the length of vector or component of vector is contravariant because it gets bigger, instead get shrink as the coordinate system and the basis. That's for covariant and contravariant. Next, I want to introduce you about Einstein notation, which here, instead we write tensor as this, we can denote the only tensor component as T mu nu here. And for a vector, we have this. Or we just write the component without a basis to evade long journey to write all of this notation. And notice that by using Einstein notation, the tensor here has matrix representation. For example, 2-rank tensor, it can make n×n matrix, not n×m because of physics and transformation in physics. And the next mystery is, what about other product operation? And again, here we use Einstein notation. The first one is dot product, or known as scalar product, or in tensor calculus we know as contraction. For example, we have this dot product, in Einstein notation, we can rewrite as this, which this dot product relate to scalar, and here we can rewrite the scalar product as this, which equals to this tensor equation. G mu nu here relate to the generalized dot product between bases or as inner product in general. That G mu nu here is metric tensor that relate to space geometry. So here, phi mu and W mu here relate to contraction. And some footnote here, if we make this matrix multiplication which represent as this tensor index contraction, then we can rewrite this contraction as this tensor, which T here relate to delta alpha nu tensor or known as Delta-Kronecker, which Delta-Kronecker here represent I or identity matrix, which by this representation, we see that G mu nu is equals to G nu mu or symmetric in index. And next, how about cross product? We know that this product is hard to non-3-dimension, but here we have tensors. So we define epsilon, mu nu, and so on until alpha here, known as Levi-Civita symbol that represent cross product in n dimension. For example, in 3 dimension, we have this Levi-Civita symbol that cross product can be defined as this contraction. And for n dimension, we have this long index Levi-Civita that n to alpha n at n dimension. So after that, we have conclusion as this, which will be our discussion in some videos. And notice that G mu nu here relate to transformation that for this case, G mu nu transform from covariant to contravariant and so on from contravariant to covariant. So tensor here has matrix representation and matrix here relate to transformation. So the next question is, what other usage of tensors instead just transformation? And that's the basics and some introduction to tensor calculus. I hope you enjoy this video. If you like this video, don't forget to share and subscribe. If you have any questions, please drop comment below. And that's it. See you later.